Welcome to homework.
Alright, so we are to draw non-isomorphic graphs given the number of their vertices n. In the first case, we are given n equals 2, and it's pretty obvious that only a single graph can be drawn with two different vertices, which would look like this. So the answer to this one would be one graph only. In the second case, we have n equals 3. Now let's see how many graphs we can draw for n equals 3. First one would be just this simple triangle. The second non-isomorphic graph would be something like this. Now, it's pretty obvious that these two graphs are not isomorphic, because if you look at, say, vertex this one, this has a degree 1, while no vertex in this graph has a degree 1. Therefore, there is no isomorphism present. And we're pretty sure that no other type of graph can be drawn with n equals 3, so the answer would be two different graphs here. Next up, we have n equals 4, and let's see how many graphs can we draw for n equals 4. First off, we have a single non-connected, like non-cyclic graph with four vertices, sorry, three edges. Yeah, so one. And second, we can draw something like this, I guess. That would change the degree of this vertex, maintaining non-isomorphism. A third, we can draw something like this. That changes the degree of this from this. Alright, next up we can draw a square with every vertex has a degree 2. Then we can just draw the diagonals of that square or that quadrilateral. Yeah, so these are all the possible combinations of non-isomorphic graphs that we can draw for 4 vertices. Therefore, for 4 vertices, we can draw 6 different non-isomorphic graphs. Finally, we are left with n equals 5. And bear with me for this one. First off, we'll start with a simple non-cyclic graph. Then we'll have some connections in between. This could be also possible. If you've read chemistry, you'll like see how it is similar to pentane and stuff. This is neopentane and isopentane. It does not matter here. I'm just making an observation. Next up, we have a graph that looks like 1, 2, 3, 4, 5, like this, and trying different permutations. This graph could be different. This could be different. You could also have two adjacent triangles. Alright, so I think we're done with triangles. Nothing else can be done with that. Next up, we'll move to squares. 1, 2, 3, 4. One vertex left. This could be the case with that. One more thing with square could be a diagonal. We could have two diagonals. We could have this other vertex lying on the diagonal vertex, right? We could also have this other vertex connected to the opposite vertex of the diagonal. You'll see what I'm trying to say. Not this thing, this, right? And we could have this with a diagonal too. Makes sense? Yeah. So in total, six such isomorphic, non-isomorphic graphs with a squarish base, and finally we can have a pentagon. That's the biggest shape you can make with five vertices. Just try different permutations. You just have to make sure that these graphs are not isomorphic in any way. So just combine the last graphs. That would also result in a new graph that is non-isomorphic, as I'm doing here. Finally, would have a star inside the pentagon, connecting all the vertices. Yep. So I hope that's all what we can draw. Let's count them. How many did we actually draw? The first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th, 13th, 14th, 15th, 16th, 17, 18, 19, 20, 21. Therefore, for n equals 5, you can draw 21 different non-isomorphic graphs. Yeah, so that's it. Pretty simple solution. You just have to count the different permutations you can have for the number of vertices.